various Zoom banners on my screen. Do you see those as well, or you just see the
No,
picture?
no, I don't see the Zoom banner, so that's okay.
Okay.
Okay, hi everyone. Welcome to the Topos Institute Colloquium. Today we are pleased and honored to have Steve Vickers from the University of Birmingham. And today he will be speaking to us about the point-free fundamental theorem of calculus. So Steve, whenever you're ready.
Well, thank you, Xiaowei, and it's a pleasure to be invited to give this talk to the Topos Institute. So, what I wanted to talk about really is about point-free topology. And those of you who know about locale theory, it's essentially locale theory, although not necessarily done in the same way. If you don't know about locale theory, that doesn't matter. There's some there's some rather subtle topos theory. So when I'm explaining what it is that I'm doing, underneath there is subtle topos theory. But I've been told that Topos Institute is basically just the name of the institute, and my audience won't all know what toposes are about. So I'm going to try and explain how you don't really need to know the subtle topos theory. It's all quite unobtrusive in the way it's done. And so that's kind of the what and the how of point-free topology. But I also want to say something about why. Why would you bother? So I'll give various examples of that. And the main result that I'm going to focus on, which is part of what happens when you try to do real analysis in the point-free manner, is the fundamental theorem of calculus. So it's a recent result of mine that is, it's just one more stepping stone on the route to having a full point-free account of real analysis. So, my screen sharing. Right, good. So, those of you who've seen ordinary topology, point set topology, will know that a space is described by giving a set of points and then describing extra topological structure on it by saying certain subsets of that are designated as open subsets. So what I'm going to describe as point-free topology differs from this is that you don't start with a set of points. The way you describe the points is you have a logical theory, and it's in the same kind of way as ordinary logic, except the logic is slightly peculiar. And that describes what the points are. A point is just a model of that theory. So what you start off with, instead of a set of points, you start off with a set of propositional symbols. These are variables in a kind of algebra of truth values. So the variables can be assigned truth values like true and false. And once you started off with those propositional symbols, then they generate more formulae using, for instance, meets, which is conjunctions, and joins, which are disjunctions. And in the logic we're going to be using, they correspond to the opens that you get in ordinary topology. And then on top of the signature, you also have a lot of axioms, and they're going to be of the shape some formula entails. That's this turnstile symbol, another formula. And the idea is that if the left-hand formula is true in some model, then the right-hand formula also has to be true. So the entails is like implies. Now, this is not that different from what you get in ordinary logic, but some of you may already have noticed that I didn't include any kind of negation or implication. And the axioms, this formula entails formula style, is slightly different from what you'd normally see, but there are reasons for doing it this way. And once you've got your head around them, it's not so different from ordinary logic. So for a model, I said the propositional symbols were like variables in a logic of truth values. You have to give them values. You assign a truth value to each propositional symbol. And once you've done that in your model, that extends to all the different formulae. You just evaluate them using the conjunctions and the disjunctions, the ands and the ors. And then what you want, in addition for it to be a model, is that for each axiom that's listed as part of the theory, each axiom phi entails psi. If phi evaluates as true in the model, then you also want psi to be true in the model. So if that happens for all the axioms, then that's what makes this truth assignment a model. Okay, so this will be clearer if I give an example. So here's the theory of the real line. So the models are just going to be real numbers. So the signature is actually two infinite families. So for each rational Q, you have two propositional symbols. One says something or other is less than Q, and the other says something or other is greater than Q. So what this something or other is going to be in the model is just the real number you're trying to describe. And then the axioms, here are some examples of the axioms. It's not a full set, but here are some examples. So one is, if your real number is less than Q, then you ought to be able to fit a rational in between, a Q prime in between the two of them. So for some rational that's less than Q, you also have your real number is less than the Q primed. So if the real number is less than Q, then big disjunction, one of these Q primes is less than Q prime. Now, that's interesting because we've already got, this is an infinite disjunction. So although I didn't stress that, I had a big disjunction. So those are possibly infinite, unlike the conjunctions, which are just finite. So that corresponds to what you see in the axioms for topology. So there's one example of an axiom for the theory of real numbers. Here's another one. If a real number cannot be both less than Q and greater than Q. So if both of those hold, then, well, that's impossible. So that the symbol on the right is falsity, impossibility. Final one that I'm describing here is, if true is true, which of course it is, then the right-hand side must be true. And this is in a situation where you've got two rationals, Q less than R. So any given real number should be either bigger than Q or less than R. So that's this disjunction here. So that's another of the axioms that you expect. So in a model, you're specifying which rationals are bigger, which are smaller than the real number you're trying to describe. And that's just describing a real number as a Dedekind cut, if you're familiar with those. Okay, so that's the real topology. Now, once we got those, sorry, having problems here with my. Okay, that works.
Okay.
So so if that was the what are the spaces? Let's try and think of some of the hows. How, for instance, and this is a big how would you describe maps from the real line to itself in terms of these logical theories? So I'm going to try and think in the style of programming languages. So in a programming language, and I'll write the definition in a box like this. So in a programming language, you first declare a formal parameter x. So you say let x be a point of R. And then we do some auxiliary calculations, blah, blah, blah. And then we define the result, f of x, as a model. So what that means is we have to specify the truth values for each rational. When is fx less than q? When is q less than fx? So at the end of this box, you say fx point of R is defined as something, something, something. All right. So that's just very schematic, but let's try it for a simple example. Here's the absolute value function from the reals to the reals. All right. So if its argument is already positive, that's just unchanged. If it's negative, you have to negate it. So it's either, absolute value of x is either x or minus x, and it's whichever of those is bigger. That's another way to think of it. So here's how we do it in the box. So let x be a point of R, and then we're trying to define when is the absolute value of x less than a rational q. Well, that only works if both x is less than q and minus x is less than q. But minus x less than q is the same as minus q less than x. So you can express it as this formula. And that's just saying x has to be between q and minus q. We also have to say when q is less than absolute value of x, and that similarly comes out as well. Either q is less than x or x is less than minus q. So I won't bore you too much with explaining that, but having written down those formulae as the definitions for every single q, you then have proved the axioms to show that it is a real number. Okay, so that's that box style is the way. I mean, what's going on inside the box? Here's the thing. You might think that it's just a very syntactic thing, and x there is a kind of hole in the definition, and when an actual parameter comes along, an actual real number, then you just plug it in to the formula that expressed down at the bottom and return a result, and there you go. But actually there's something a little bit more interesting, which is you've actually got a new mathematics inside the box. So the first way you can see this is that in ordinary classical mathematics, you've just got two truth values, true and false. But here in the box, we've got far more. For every rational, we've got a standard truth value saying x is less than q, and another one saying q is less than x. X is the real number that we declared as the formal parameter. And the way to think, I mean, this might seem puzzling, but the way to think of it is that they don't express whether something is true, but rather they say where something is true, for which models, for which values x it is true. So you've got all these different non-standard truth values. So that's a new mathematics itself. Another one, and this is very deep, comes in because we actually want to define continuous maps. The whole point of this stuff is really it's for defining continuous maps and maps that respect topology. And the continuity turns out to amount to having a different logic. It's not the usual classical mathematical logic. It's a different one. So let's see how this works. Continuity in topology says that the inverse image of every open is itself open. All right, lots of you are probably familiar with that from topology. Now, the way that works in this logical setting is, well, what does it mean to have the inverse image of an open such as x less than q? That's basically just saying that f of x is less than q. So what we're saying is this thing also has to be open, and that means it's made from truth values of the form x less than r, s less than x. Those are all the ones we were given, using these special topological logical operations of and possibly infinite or. And similarly for q less than fx. So the approach to getting that, to make sure that we do have continuity, is to restrict the mathematics inside our box so that we only have limited ways of constructing our f of x. We started off from all these extra truth values, the ones that were described up here. And now we're allowed to combine them just using our ands and our ors to describe what f of x means. So this is a different logic. So, well, what is this logic going to be? It's called geometric logic. And inside the box, the mathematics of the sets is going to be highly restricted. You're allowed finite limits, so limits are equalizers and products. So I guess you're familiar with those things. Also, arbitrary colimits. So the arbitrary corresponds to the arbitrary for the disjunctions, for the ors, the possibly infinite ors. It also includes natural numbers, n, the rationals, q, free algebras. But what it doesn't include is function spaces, for instance, y to the power of x, all the functions from x to y. Doesn't include power sets, p of x, all the subsets of x. Doesn't include the real line. They're not going to be sets in the set theory of inside the box. So they have to be dealt with instead as point-free spaces, which in fact is what I'm explaining to you how we do. And there's a corresponding logic that's also very restrictive. We've got the finite ands, the arbitrary ors, got equality, we've got existential quantification, but not negation, not implication, not for all, except they do crop up implicitly in the logical axioms. So if you say phi entails psi, and now I've got I've extended this a bit. That Q subscripting the turnstile, that is essentially meaning for all Q. So for all Q, phi of Q implies psi of Q. So there's sort of one level where you can put in these other bits of logic. And also, I mentioned these things that are kind of given there. They're built-in sets that you're allowed to use. You can often do away with the infinite disjunctions, avoid those by using there exists with an infinite set. So the axiom I mentioned before with the it's over here with the infinite disjunction, you can replace that over all possible q primes less than q. At least one of them works. You can express that as there exists q primed such that it's less than q, which is what we wanted down there, and your model is less than q prime, which is there. Okay, so I've just presented those as a rather ad hoc set of restrictions they might have. There's some rather deep topos theory going on underneath, and I ought to say something in explanation of that, just to prove that I'm not bullshitting you with these axioms. But if you're not used to toposes, you might just prefer to look at this cute picture of a wombat. So you do that, but the rest of anyone there who understands toposes, I will just say this maths inside the box that I was describing informally on the previous slide, that is the internal mathematics of a classifying topos. So it's the S of X, where X is the theory, X is the space of models. So it's the classifying topos for that theory. Except it's not all the topos mathematics. It's just the geometric fragment. It's that part of it that's going to be preserved by inverse image functors. And then a map, as I was defining it, is going to be a geometric morphism. And it's the universal property of classifying toposes that makes all this work. Then, okay, so that's sort of basic topos theory. And then for any of you who are interested in constructive topos theory, maybe you already know the classifying topos is a slightly slippery construction because it depends on choosing some base topos, S, which I've kind of smuggled into the notation up there, which in effect tells you what infinities you're allowed for infinite disjunctions, and won't necessarily be a classical topos of sets. So one way of avoiding that dependency is to work as far as you can without infinite disjunctions, and do the kind of substitution that I showed you. And I've got a couple of references down here that show you that can tell you more if you want to know. Okay, so that was the how all this is, all the point free topology is done. And I'll just say something about why. This is quite a lot of effort to give up your previous ways of doing mathematics and think of trying to do it using the geometric ideas instead. So why would you bother? So the first one I'm going to say is that once you get onto first order geometric theories, so that's where you've got variables and you've got their exists, quantification of things. You're actually able to define spaces much more general than those that you have in point set topology. So lots of proper classes can be expressed as point free spaces. So for instance, you've got a space of sets from what's called the object classifier. You've got a space of groups. And that leads on to the second reason for, why you might want to do it this way. And this is about bundles. So if you think of tangent bundles, you've got some manifold, and at each point you've got a tangent space. That tangent is going to depend on the point in the original manifold, and it in some way is going to vary continuously with the point where you're taking it. But there's no natural way in point set topology to show what this continuous variation means. But now we've got the geometric ideas, and now we've got the generalized spaces that come from the previous slide. We can actually define spaces of presentations of geometric theories. Okay, so to define a space, you've got to define a geometric theory. What does that mean? How do you present it? You've got various spaces of presentations. So one example is you've got a space of sites which crop up in topos theory. And then the presentation itself defines the space. So think what happens if you do this in the box world. Once you've declared x is of sort, x is a point of x, in that box, you've defined a space by showing how to present it. You can see this in two ways. So the first way is as a bundle, bundle in a sense of for each point, you've got a space. So for each point of x, you did it for that formal parameter little x. For each point of x, you defined a point of a space of spaces. You defined a point of that space of presentations. So this then turns into, by the previous reasoning, turns into a map from big X to the space of spaces. So that says for each little x, you've got a space which is the fiber over little x. So that's the bundle view of what you're doing inside this box world. But the second way is that you also get a forgetful map from X, because what you've done in the box world, X itself was a space. X itself had its own theory. So what you've done inside its box world, in effect, is to extend this theory to make a new, bigger one, whose models are pairs. First component is point from X. The second component is a point from the fiber that you've just defined. So this extended theory gives its own space, and there's a map to X that just forgets the Y component of it. So this bundle, continuously indexed family of spaces, which is what this stuff really defines, has turned into bundle in the other way of thinking of it, which is a map from some upstairs space to a base space. And this all just works out very naturally in the point-free approach. And I think this must be one of the biggest potentials for why you would want to do point-free topology. And I did there's some topos approaches to quantum structure, and I did a paper with Sander Volter and Bas Spitters to show how to use geometric techniques to study some bundle aspects that appeared in that. So, okay, so that's the why. So, and now want to move on to the big example, which is the point-free real analysis. And I hope by the end of the talk, I'll have managed to persuade you that actually it doesn't look that much different from ordinary real analysis, but maybe it's got some funny techniques in some places. So one funny technique is, I'll say more about this, it's about using one-sided reals. What I showed you before, Dedekind sections, were two-sided reals, but if you just take half of a Dedekind section, you've got what appears as a one-sided real, and they turn out to be very useful things to look at. Another one is hyperspaces. So these are spaces of subspaces, and we also get analogous spaces of measures. So the example I'll tell you about, the fundamental theorem of calculus, we're going to have to deal mathematically, leaving aside the logic, we're going to have to deal with both integration, and I'll use both lower and upper integrals to approximate that, and differentiation. And I'll do that in a Carat-Theodori style. So why is this? Well, the fundamental theorem of calculus is, if you remember it, it says integration and differentiation are reverses of each other. So somehow in a geometric setting, we've got to talk about both integration and differentiation. And there's already quite a big body of work. You see some of the references here go back to 2008, 2009 that say something about these point-free. But it's only more recently, and my student Ming doing my former student, he's finished now, but he did his thesis on with quite a lot of point-free analysis as mathematics that needed to be done in order to get to the number theory that he was interested in his thesis. So he defined as point-free as real valued maps, exponentiation, and logarithms. And then since then, I worked out the fundamental theorem of calculus, the FTC, to get the calculus results for exp and log. So I'll start off saying something about one-sided reals, because they're kind of, they crop up all over the place when you're doing the point-free analysis. So what they do is, you remember we had two sets of opens, Q less than your real and real less than Q. And if you separate these out, if you just take the first ones, you get only half the topology. You get the topology of lower semi-continuity, and the other ones you get upper semi-continuity. So point-free, you get two different spaces of lower reals and upper reals. So the lower reals I'm going to draw with this arrow going to the right for reasons that I won't explain now, and the upper reals goes the other way, and they also have to include some infinities. And then a Dedekind real, right? One way to express it is that it's got a pair, it's got a lower half, x under bar, and an upper half, x over bar. And these individually satisfy all the axioms that make sense if you're just dealing with one of them on its own. But then you also have to glue them together. So two more axioms, which you've seen earlier, that mix together what's going on with the lower part. What's going on with the lower part there and what's going on with the upper part. So you've got the lower and upper reals that you can deal with in themselves, and then you have to combine them, put them together with some more axioms to show that they make a Dedekind real. So one way to think about these two, the lower part shows how your x is approximated by rationals from below, and the upper part shows how it's approximated from above. So here's quite a useful strategy for doing point-free real analysis. You deal separately with the lower and upper parts because they're simpler to deal with. There's less going on. And then you show them that they fit together by proving the two real axioms. But there's a big limitation for this, and you need to be aware of this because it governs the particular routes that you take. The limitation is all the maps from, let's look at the lower reals, from the lower reals to itself, they have to be monotone. That's just a simple consequence of what continuity means in the topology of lower semi-continuity. And similarly for the upper reals. So this tells you something limiting about the arithmetic. You can't subtract lower reals and expect to get a lower real. So if you try to do x minus y, this would be not monotone, but antitone, reverses the order in y. And you can't do that. Similarly, if you want to multiply two of them, x and y, you can't do that if one of them's negative, because then the multiplication would be antitone in the other. So they both have to be non-negative. And that works well, as Ming showed, for exponentiation and logs. More generally, we often need to separate out the signed parts by sort of more combinatorial means. And we'll see how this works later with integration. Something I want to touch on briefly, because it does come into the fundamental theorem of calculus, is hyperspaces. So I used to call these power locales, but I'm trying to standardize on the topological terminology. So a hyperspace, given one space, a hyperspace is a space of subspaces of the given one. So we got the Vickers hyperspace. If x is given, then Vickers hyperspace is Vx. And that's a space of certain compact subspaces of x. And Vickers already defined that topology in a point set version. So it's not straightforward to make this work point free, but once you've got it, it's fairly intuitive to use. So an example is the Heine-Borel theorem, which says that a closed interval is compact. Well, that comes along with a continuous map that takes two Dedekind reals, the first one less than or equal to the other, and gives you the compact interval as a point of the Vickers hyperspace. And this shows that the hyperspace, this gives a natural sense in which the closed interval depends continuously on x and y. You've got a continuous map to the VR, the hyperspace. I'll skip over the bit about the tautologous bundle because it doesn't really add much to the example we've got. And I'll go on to integration. So if you think about how integration is done, the most natural definition of integral is counting squares. And you can count squares underneath the graph, and you can count squares underneath above a graph, and you have to make the squares smaller and smaller until they approximate each other. So that's a natural application of having lower reals for the lower integrals approximated from below, and the upper reals for the upper integrals. So let's look at the lower ones. All right, let's call it integral sign under bar for lower, x over some space. F now is the integrand. That's a map from x to reals. And mu here is going to be a measure. I'm not quite using measure theory, but I'll say what I am doing. So first thing to notice is that we're multiplying. We want to do it in lower reals because we're doing lower integrals, and we're trying to multiply two of them together. So they better both be non-negative. So f, the integrand, is a function from x to non-negative lower reals. The measure mu, well, it's going to be what we call a valuation. So this is like a measure, but it's just defined on the opens, and it takes its value in lower reals. And it has usual sort of properties. Mu of the empty set is 0. Add together two mu's, mu u and mu v. You can rearrange it. You get the same answer as if you'd taken mu of the conjunction, the intersection, added with mu of the union. And we also need a continuity, which, if you know what directed joins are, it says it preserves directed joins, and that's the best way to think about it. If you don't know what directed joins are, then it says that mu of an infinite union is the sup of the mu's of all the finite unions you get by taking finite subsets of the indexing set. But I won't dwell on that. Okay, so the lower integral can be evaluated, 0.3. It's not completely obvious how to do it. It's a bit more like a Choquet integral than a Lebesgue integral, but it's that's all been done. Upper integrals are not, they're similar, right? So now the integrand has to be valued in upper reals. Nu is now a co-valuation. So nu of u is the measure of the closed complement x minus u, but that can all work. And then the upper integral can be defined. And one thing that comes out of this, right? You remember I mentioned hyperspaces. Well, there's a valuation space. Given x as a space of valuations on x. And this is, if you know about the Giry monad for measurable spaces, it's like that. And there's another one for co-valuations. So that's going to be interesting because it makes sense of statements that some valuations or co-valuations are defined continuously, parameterized continuously by some parameters. So once we've done that for the one-sided time version, we want to be able to combine it for two-sided Dedekind ordinary real numbers. So let's look at integral over a space x of an integrand, which is now a function from x to non-negative reals, Dedekind reals, with respect to mu. Now, mu is still actually it's still actually a valuation with values in the lower reals. But now we ask for it to be finite. We want mu of the whole space to be not just a lower real, but to be Dedekind. And once we've got that, then it also has there's a co-valuation that goes with it. You just subtract the valuation from the total value of x. So what we can do, and this is, I write this, not mu. So here's the basic theorem. This is actually the hardest calculation in my paper. All right. So it's just kind of intricate, but everything else hinges on it. So if x is compact, f is a Dedekind valued integrand, this function. Mu is a finite valuation. Then we can construct the lower integral, the upper integral, put them together, and they make a Dedekind real. So that means we've managed to define the whole integral as a Dedekind real value, right? Integral over x of f with respect to mu, it's a Dedekind real. Now, this is just non-negative stuff. So we really want for assigned f's valued in a whole of the real line. That's not a big deal, really. So we just split f as a positive and a negative part, and f is got by subtracting one from the other, and we just do the same with the integrals. So once we've got that, here's the way we can define Riemann integrations. So we first define the Lebesgue valuation. Can do that. 0.3 geometrically. Now, if x and y are reals, with x the smaller, s less than or equal, that induces a Lebesgue measure, Lebesgue valuation on the interval between the closed interval between them. So it's a point of the space of valuations of that space for the closed interval. And we can now define our integral in a more usual notation with lower and upper limits x to y of the integrand f of t dt. So that's basically calling up the Lebesgue valuation. It's the integral over the closed subspace of f with respect to the Lebesgue valuation. For general x and y, that was for x less than or equal to y. We can really get the more general ones just by defining from the minimum to the maximum, and we have to correct the sign. And there's a bit of care needed to do this geometrically. We can't just do a case split, but that's one of the things that one of the classical things you can't do geometrically, but in this case we can do the definition. And then of course we need to know for any x and y, the integral between x and z is the same as the sum of from x to y and from y to z. And then once that sets us up for a whole load of integration in the fundamental theorem of calculus. Okay, now going to have to do differentiation as well. So this is done in the Carazzetto-Dori style. Instead of talking about limits, we talk about having a continuous slope map. So it's a map of two variables satisfying this equation, right? Oh, sorry. So you can see if y is not equal to x, you can divide and you see exactly what the slope map has to be. But the interesting thing, of course, is when x equals y. And then the usual derivative using limits is just got by saying, well, we want the slope map to be continuous. And then the derivative is the slope map applied to x and x. So how do we define those? And turns out integrals are really useful. So here's the theorem. The f is defined on some real open interval as an integral from some fixed x to a variable x of function g. Then the theorem says f is differentiable. If you differentiate it, you get back to the original g. So this is part of the integration and differentiation being reverse of each other. So what's the slope map? If x is less than y, then it's easy. We know what it has to be. We can write it down from the defining formula. And then we can calculate with respect to the Lebesgue integral. But then now here's the trick, and I haven't seen this elsewhere, and it's not that hard, but it turns out to be really cute. So on here, we've got the Lebesgue integral over the interval xy divided by the length of that interval, so y minus x. Well, that's just the uniform probability valuation on this interval. So uniform probability probability means total mass is one. So this is what we're actually going to use because that makes sense even when x and y are equal. So then the interval is just a single point, 1, and the integral of g with respect to the uniform measure is just the value of g at x. That just drops out easily. So geometrically, we can define this uniform probability measure, covers all the cases x less than or equal to y. And because everything's geometric, everything's continuous, that means that includes the domain of integration, the closed interval. It includes the valuation we've just defined. So the slope map we defined on the previous page varies continuously with x and y, even at the limiting point where x equals y. And that is all you need to get the fundamental theorem of calculus. And using the existence of integrals, that gave the explicit slope map. There's a converse, right? Which I'm not going to go into the details, but it very standard proof uses Raleigh's theorem. But fortunately, I'd already proved that in 2009, and so we get the second part of the fundamental theorem of calculus also comes out. Okay, so can we apply this to exponentials and logarithms? Well, yeah. So here's how to prove that the logarithms are, which Ming had already defined in his thesis, how to prove that they're differentiable. Let's define, this isn't the logarithm that Ming defined, which was the inverse of exponentiation. This is natural logarithm defined as an integral. So standard thing to prove is that that's a homomorphism that converts multiplication to addition. It's not hard to prove a lemma geometrically, saying if you get any homomorphism like that, then f applied to any gamma to the y is equal to y times f to the gamma. So use algebraic laws of exponentiation when y is rational, and then use density of the rationals. So putting x equals gamma to the y, you get fx equals this, and that shows that log to any base gamma of x can also be defined as an integral, and I can use fundamental theorem of calculus. And once that's done for the logarithms, you can use chain rule to get it for exponentials as well. Okay, so that's all I can say about the fundamental theorem of calculus. I'll just say a couple more reasons for how, a couple more pleasing features that come out of doing it geometrically. So they are instances where it seems to provide new, fresh insights into classical results. So Ming, in his thesis about number theory, he studied Ostrovsky's theorem, which is a number theoretic result concerning things called absolute values on the rationals. So they're analogous to the ordinary absolute value function, but there's a whole load of extra p-adic ones that come out of number theory. Geometric reasoning says, well, why not use the one-sided reals, see where they go? And it turns out this automatically includes, unexpectedly, some things called multiplicative seminorms, which are interesting in themselves and have connections to something else called the Berkovich spectrum. So Ming is now exploring those connections, see how far they go. Here's another one. I won't really say anything about this. I think my time's over. Well, no, I'll just say something.
It's okay, you can keep going. Thanks.
Okay, so this is about Minkowski's space-time. So usually it's thought of as just Dedekind reals, four-dimensional, with the usual topology, but it can be split into two parts. They're analogous to the lower and upper semi-continuity topologies for the reals, but they respect the relativistic space-time structure. And in each one, you find what's called the specialization order of the topology matches the causal order of physics, this is relativistic ordering that you get in points of space-time. And you also get infinite points arising. So I briefly mentioned that lower reals have to include a plus infinity. When you see what happens with Minkowski spacetime, it turns out you get infinite points arising there, and they match some ideal points that have been identified by physicists. So this is a construction by Geroch, Kronheimer, and Penrose. So just automatically out of the point-free topology, you recapture some things that physicists already knew about. So I'm currently exploring these spaces to see how much else of their intrinsic structure has physical significance. And with that, the rest is all just references. So with that, I'll finish my talk.
Thank you, Steve. Thank you, Steve. So
Yep.
we will now have questions for Steve, and there are two ways to ask questions. One, you can raise your hand in the Zoom chat, and then I will call on you to lower your hand, or you can ask your question in the meeting chat, and I will ask on your behalf. Okay. Yes, I see one hand going up. Kevin, I see that you have a question. Can you unmute yourself?
Sure. Yeah, thanks a lot, Steve. Very intriguing. Kind of in line with the example applications we were just giving, in talking about these upper and lower rails, we couldn't help but think about directed algebraic topology, kind of algebraic topology, trying to give a more geometric model of infinity one categories in the way that topological spaces give a geometric model of complexes. I wonder whether this directness could be relevant in that direction. Do you have any idea?
That's a very interesting question. I've sort of thought sometimes about directed algebraic topology, but not really got very, very far into it. I suspect it's something that I would hope some aspects of that will emerge as we understand these structures better. I mean, again, I would hope this is some of the fresh insight that arises once you start doing things point free. But at the moment, I don't know.
Great, thanks.
Right. Thank you, Kevin, for your question. Are there other questions in the chat? So, Steve, I have a question.
Yeah.
I think you talked a little bit about probability at some point towards the end of the talk, and I mean, it seems like you have built up all the machinery needed to do probability theory. You have integrals, exponentials, logarithms, and maybe even you could even do information theory on this. I'm just wondering if you've thought about like point-free version of probability theory, and like I think one of the issues that people are trying to solve in quantum mechanics is that you sometimes don't have a global sample space in your quantum models, and it seems like using a method you could maybe do away with that global sample space that we have to start out with in probability theory, measure theory. Do you have any thoughts about that?
Okay. This is subject to the proviso, of course, that what we have here, point free, is not about arbitrary measures, but only about the valuation. So these really correspond to regular measures. And I think when, I've looked quite a lot at quantum theory, not saying I'm an expert in it, but I've looked quite a lot into it, and you find quite a lot of the probability stuff is about taking, when you look at proper descriptions of von Neumann algebras and that sort of thing in terms of probability theory, that there's a lot that is about how to get the generality of arbitrary measures, and I would suspect, I would hope that the valuation theory enables you to get to a part of that, a fragment of that, that is still meaningful and still significant, but doesn't get as complicated. That's my, I don't know if this is me hoping that things I'm not an expert in are simpler than than they look, which is very easy to do. But I'm hoping that just using evaluations, using the slightly simpler theory, will still get results that are relevant to the probabilistic phenomena that occur in quantum. So, I mentioned the paper I did with Spitters and Volters. So that this was connected with a project I was running at Birmingham a while ago about applications of geometric logic to quantum theory. One of the things we were trying to do there and was to describe the Born rule just in terms of the point-free space. Now there were, the sort of intriguing things there, we didn't quite manage to pin it down, unfortunately. There's some things with discontinuity that we never quite solved. So I can't claim to have got there, although I'm interested enough in it to think, well, it wasn't entirely misguided. There's something there. So there's a paper there I did with Fauser and Renault.
Was it one of the references in your slides that you mentioned?
No, you can find it on my website.
Oh, okay.
Yeah.
Thanks. Yeah. Great. Yeah. Thanks so much, Steve. Yeah, I'm looking forward to if you have other results on this, I'll be looking forward to that. Do we have other questions in the Zoom chat, Steve?
Shall I look?
Okay.
Nope, nothing I can see.
Yeah.
I had one more question, if that's all right, shall we?
Yeah, sure. Go ahead, Kevin.
I was just wondering, so it seems like you could treat this story as fitting into the story of convenient categories for topology. That maybe in some sense you're saying a convenient category for topology is the category of classifying toposes of geometric theories or something like that. I don't know if that's a ridiculous way to think about it, but I was wondering what we know about this category. We can do lots of great constructions within each classifying topos, but I really have no idea what the properties of the collection of all spaces in your sense are going to be like.
Did you say convenient categories?
Yes. So in particular,
that's like it's like when you go to the compactly generated topologies in order to get something Cartesian closed. Is that right? Have I got the right idea?
A big desideratum, right, is Cartesian closure, and I'm guessing we probably don't get anything like this on this category of classifying geometric theories. But I have no idea what kind of things, how nice of a place to think of this as being.
I know Martin Escardo for a while was looking at compactly generated topology, trying to do that point free, and they didn't. I hope I'm summarizing, summarizing the end point of the story. They didn't seem to work out as nicely as he had hoped. But perhaps, if you contacted him, he might tell you more about that. But that's
Sure.
specifically about compactly generated. He got some definite results there. But yeah. Can you elaborate
Yeah,
on?
I guess.
Give me a bit more to go on the question.
Yeah, I guess I'm just wondering. So, should I think of the category of classifying toposes of geometric theories
Yeah.
as something you're proposing as a category of spaces?
Yes.
And if so, how good of a category is that? I mean, I know Grothendieck toposes are all right as a category overall. Is this thing going to be? Do I have some reasonable selection of limits and co-limits and things of spaces in here, for instance?
Yeah. Okay, so I said something, on the wombat slide. I said something about trying to do this stuff, the topos theory, constructively. I mean, there's a perfectly well-known theory of Grothendieck toposes over an arbitrary base space. Actually, you'd better have natural numbers objects, or you don't get very far. So, and if you look in the elephant, there's a whole section on B top over S, which is basically about um, the categorical property, two categorical properties that you get there. So you've got pretty much all the two limits, two categorical limits and co-limits that you would
Right.
want. And the kind of also the elephant shows how to account for infinite co-limits in terms of indexed categories. So it shows how the objects of your base topos S can be thought of as indexing co-limits that you then get in the B top over S. Are you following me?
Yeah.
Yeah. So now I did something about using the natural number object and the free constructions as a way to do away with the infinite co-limits. So just having the finite co-limits and these universal algebraic constructions. I was seeing those as the properties of the internal maths of a arithmetic universe in the sense of Schweier. So I did write an account of what the geometric theories would look like in terms of a very foundationally minimal setting, how they would look like in the arithmetic universes. And then I showed how if you want to relate those to the toposes, B top over S, arbitrary base topos, then you can do that. And it actually uses there's some interesting alternative descriptions of geometric theories that you see in the elephant that aren't the usual, geometric theory is first order theory with blah blah blah. It's much more deeply categorical than that. So I showed how to relate that stuff to the stuff without the infinite co-limits, but with the arithmetic universe constructions. Is that? I don't.
Okay, yeah, yeah.
I'm sort of burbling a bit. I don't know if this is answering your question or just going off.
Those are some interesting pointers, definitely. And yeah, go look in the two category theory part of the elephant. Is always a good answer. Yeah, thank you.
Yeah. Okay.
Thank you. We have one question on YouTube. So it's from DMac, and his question is, in relation to Ostrowski's theorem, how would the real absolute value make sense as the valuation of the prime at infinity?
God, I think perhaps Ming should answer this since he's in the audience. But
feel free to unmute yourself, Ming, or Steve, you too. You can answer this.
Say again what the question was.
Okay, in relation to Ostrowski's theorem, how would the real absolute value make sense as the valuation of the prime at infinity?
The prime now, which is the prime?
I guess the ideal point at infinity.
The ideal point in infinity. So I was sorry. The sort of in the paper that I did with Steve, there were sort of two different kinds of absolute values. And one of it was valued in the upper reals, right, which allowed for certain degeneracies, and the other one that was valid in the Dedekind reals, where we didn't have anything that corresponded to the infinity. Um, so when he says infinity, does he mean like when we take like because the absolute values that are equivalent to one another are equivalent up to exponentiation? Does he mean that we take one of the exponentiation up to an infinity sign? Is that what he means? Or
I'm sorry, I'm not sure. Yeah,
I think
but I guess
maybe I can clarify.
yes.
It's traditional in number theory to think about the real absolute value on Q as happening somehow at the quote unquote infinite place, where all of the p-adic values are at.
Well, yes. Okay. So the question is like, what is the picture of? So what are the implications of the point free picture for this number theoretic perspective that the real prime corresponds to the point in infinity? Is that right?
Probably, yeah. I think you could interpret it that way.
Oh, okay. Well, yes, that's a really nice question. So, one of the interesting things that sort of emerged in my thesis is that this sort of particular view of viewing the real prime as sort of corresponding to the point infinity is actually not quite the same picture that we get in the geometric picture, and that has a lot to do with like the subtleties of quotienting that occurs. So, in the case of well, in Topos theory, let's just say it's sensitive to the difference between quotienting a space by a group action versus a monoidal action. And if you look carefully at the space of absolute values, if it's non-Archimedean, then it's acted on by a group action from 0 to infinity. But in the case of an Archimedean absolute values, the ones that correspond to the real place, it's only acted on by a monoidal action. Because if you try and exponentiate it to something that's bigger than one, then you destroy triangular inequality. And so this sort of forced us to use a particular kind of topos theoretic construction called lax descent. And what we found was that, this sort of, informal view in the number theory of viewing the real prime as a point infinity, actually it corresponds to this sort of a blood interval, by which I mean it's an interval of the upper reals from 0 to 1. So yeah, so this is an interesting perspective because it's sort of like, it overturns, a long-standing assumption in number theory. And more broadly speaking, one of the things that I was interested in is that, in number theory, there's sort of this guiding principle of the local global principle where we should think about, there's a big problem. It's really hard to solve. Let's break it up into tiny pieces and then we can solve all the pieces and put them back together again. And in the case of a lot of number theoretic questions of interest, we want, by Ostrowski's theorem, we want to break it into the p-adic pieces and the real pieces. And a lot of techniques work well on one side, but not on the other side. And, there's a lot of thought and a lot of energy directed towards trying to figure out how do we sort of create a unified framework that accommodates both the differences, but also respects that, those two things are different and makes visible some of those differences. And an interesting perspective, so this is a part of a preprint that I'm currently trying to write up, and it's joint with Steve, is that, if you look at the places which correspond to the equivalence classes of these absolute values, in the case of the non-Archimedean or the p-adic absolute values, you get singletons, which is what you would expect in the classical case. But in the case of the reals, the point infinity actually turns out to be a blood interval. Somehow, somewhere, there's some sort of intrinsic topological structure that is invisible if you thought about things classically, but somehow it becomes visible when we think about things in a point-free perspective. So it dovetails with this sort of general theme of, Steve was sort of, giving various remarks about, why think about the point-free perspective. Well, one thing that I found really interesting was that there are certain things that are that are sort of invisible in the classical perspective, but then certain subtleties emerge once you restrict to this sort of very particular and very unique perspective of point-free topology. So yeah, I hope that gives a reasonable sense of well, the picture.
Yeah, I like that a lot. I mean, thank you so much. Thanks for the answer.
I could add some. I mean, I could add something that. I mean, Ming was going into some details there, but just my sort of broad overview of what's going on. I found it quite interesting that when we went to the upper reals, we've got at one end we've got the Archimedean absolute value, the usual real valued one, but that that kind of splurged out so that in the limit it became the trivial absolute value, and then that merged into the p-adic absolute values, and you keep going. At the end, we also had to put in the multiplicative seminorms that then corresponded to finite fields. So we've got those cropping up automatically, and it was sort of the way it all appeared in a continuous spectrum that doesn't quite work when you're using the Dedekind reals.
Yes, yes. Yeah, maybe also a quick remark is that both Steve and I have thought a little bit, but not in too much detail, about the connection with the condensed mathematics. It seems, yeah, I don't want to claim any theorems about this particular, but it was rather interesting that there was sort of an interesting kind of scaling phenomena that also was sort of emerging in that context when Schulze and Clausen were looking at liquidification, I think it was called, but okay, let me claim no theorems and just say that strange scaling phenomena seems to occur when we think about the Archimedean place, and maybe there's something, maybe this is pointing towards something delicate that we should take seriously. Maybe it's not just a point at infinity.
Well, very cool. I love that intriguing connection to condensed mathematics. Well, thank you very much, Steve, for your talk today, and thank you for answering our questions. I'm going to end the live stream now, and then we will continue in Zoom, over Zoom. Okay, the YouTube live stream has ended. So do we have any